The dominant theory of the origin of the universe centers around a cosmic cataclysm physicists call the Big Bang. The Big Bang theory arose from the observation that other galaxies are moving away from our own Milky Way galaxy at great speeds in all directions. The theory offers a comprehensive explanation for a broad range of observations of a cosmic phenomena, including the abundances of light elements, the cosmic microwave background, radiation, the large-scale structure, and Hubble's law. Our current understanding of the nature of the universe and its subsequent evolution largely depends on the work of perhaps the most popular scientist of all time, Albert Einstein. Einstein's general theory of relativity describes spacetime by a metric which determines the distance that separates nearby points. The points, which can be galaxies, stars, or other objects, are specified using a coordinate chart or grid that is laid down all over spacetime. Einstein had just developed his general theory of relativity in 1916. An interesting time because he had developed that theory, which was the first theory of not just how objects move through space but how space itself could expand and contract and be dynamical. A remarkable theory that told us that space curves in the presence of matter, and it was beautiful, and he kind of knew it was correct, but at the time it disagreed with observation. And the observation was that the universe was static and eternal. That was a conventional wisdom in science at the time, that the universe had been around forever and would be around forever, and his theory didn't agree with that because his theory, general relativity, suffered from the same problems that Newtonian gravity suffers from. Gravity sucks, it always pulls, it never pushes, and if you put stars and galaxies out there, they will not just stay there. Gravity will produce a universal attraction that will pull them together. Since the universe has a finite age and light travels at a finite speed, there may be events in the past whose light has not yet had time to reach us, and because space is expanding and more distant objects are receding ever more quickly, light emitted by us today may never catch up to very distant objects. According to the Big Bang theory, the universe at the beginning was very hot and very compact, where it is thought that at a such incomprehensibly dense energetic state the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were forged into a singular force. Since then the universe has been expanding and cooling down, so the natural question arises, if this trend of cooling down and expansion continues, how will the universe end? If the universe is really expanding, then you don't need a cosmological cause anymore. If the universe is expanding, gravity can be universally attractive and just slow the expansion, and the big question of 20th century cosmology became, is there enough gravity to stop the expansion? How will the universe end? Will it end with a bang or a whimper? Will it end with a big crunch, the reverse of the Big Bang? Or will it expand forever? Factors that need to be considered in determining the universe's origin and its ultimate fate include the average motions of galaxies and the amount of dark matter and dark energy that the universe contains. Another strong factor that determines the ultimate fate of the universe depends on its overall shape, how much dark energy it contains, and on the equation of state, which determines how the dark energy density responds to the expansion of the universe. There is a strong consensus that the shape of the universe is flat and that the universe will continue to expand forever. The ultimate fate of the universe is determined by its density based on measurements of the rate of expansion, and the mass density data favors a universe that will continue to expand indefinitely, eventually becoming too cold to sustain life, resulting in the Big Freeze universe. The Big Freeze, or called the Big Chill, is a scenario under which continued expansion results in a universe that asymptomatically approaches absolute zero temperature. As existing stars run out of fuel and cease to shine, the universe will slowly and inexorably grow darker. Eventually black holes will dominate the universe, which themselves will disappear over time as they emit Hawking radiation. The Big Freeze scenario is gaining ground as the most important hypothesis. However, observations are not conclusive, and the alternative models for the ultimate fate of the universe are still possible. Scientific progress relies solely on the carefully constructed data gathering process through experimental observation. Luckily for us, the universe has a vast cosmic arena from which we can derive data from. There are enough galaxies that if you put your hand up in the night and looked in a dark spot in the sky and made a hole the size of a dime with a large enough telescope, you could see 100,000 galaxies, and that means that even those stars explode once every 100 years per galaxy in that little region with 100,000 galaxies. On a given night you'll see 10 stars explode. The universe is huge and old, and rare things happen all the time, including life. Observations of the cosmic background radiation by the Wilkinson microwave anisotropy probe and the Planck mission suggests that the universe has a significant amount of dark energy. In this case, the universe should continue to expand at an accelerating rate. The acceleration of the universe's expansion has also been confirmed by observations of distant supernovae. Our new picture of cosmology is that we live in a universe dominated by nothing. The largest energy in the Universe 70% of the energy in the universe resides in empty space, and we don't have the slightest idea why it's there. The vast spaces between galaxy filaments are known as cosmic voids, which contain very few or no galaxies at all. Voids are believed to have been formed by a baryon acoustic oscillations in the Big Bang, collapses of mass followed by implosions of the compressed baryonic matter, starting from initially smalls anisotropous from the quantum fluctuations in the early universe. One of the more fascinating findings in the cosmology is that, as far as quantum mechanics are concerned, not even voids are completely empty. If you take empty space, and that means get rid of all the particles, all the radiation, absolutely everything, so there's nothing there. If that nothing weighs something, now that sounds ridiculous. Why should nothing weigh something? Nothing is nothing. The answer is nothing isn't nothing anymore in physics because of the laws of quantum mechanics and special relativity. On extremely small scales, nothing is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a timescale so short you can't see them. The point is that we can't measure virtual particles directly, but we can measure their effects indirectly, and in fact they're responsible for the best predictions in physics. This is the space inside of a proton, the empty space inside of a proton. This is an animation, but it's an exact animation coming from physical calculations. This is what the space looks like now. How do we know that? Well, there are a lot of reasons, but one of the things are, it turns out most of the mass of the proton comes not from the quarks within a proton, but from the empty space between the quarks. These fields popping in and out of existence produce about 90% of the mass of a proton, and since protons and neutrons are the dominant stuff in your body, the empty space is responsible for 90% of your mass. So these empty space is vital to science, and these calculations are vital to understanding not just protons, but electrons and atoms, and produce the best comparisons, and I will repeat this, the best comparisons between theory and experiment in all of science to 10 decimal places in quantum electrodynamics. Using these calculations we get the right answer. It's amazing. The observational universe is 13.8 billion years old, about 155 million years after the Big Bang the first star formed. Since then stars have formed by the collapse of small dense core regions in large cold molecular clouds of hydrogen gas. Stars of low to medium mass, such as our own, will expel some of their mass as a planetary nebula, and eventually become white dwarfs. More massive stars will explode in a core collapse supernova, leaving behind neutron stars or black holes. Although some of the star's matter may be returned to the interstellar medium, a degenerate remnant will be left behind. Therefore, supply of the gas available for a star formation is steadily being exhausted. The understanding of star formation and the life cycles of stars has profound implications, not only for the origin and the ultimate fate of the universe, but also for our origin and how we came to be. Cosmology reveals how we are made from star dust. The amazing thing is that every atom in your body came from a star that exploded, and the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You couldn't be here. Your stars hadn't exploded because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution, weren't created at the beginning of time. They created the nuclear furnaces of stars, and the only way they can get into your body is if the stars were kind enough to explode. Thanks for watching. Did you like this video? Then show your support by liking, subscribing, and ringing the bell to never miss videos like this. You